Hi everybody. Today we will consider solution of some problems on the topics that we discussed at the last lecture. And the first problem will be something like this. A long bar of given mass m and given length L stands on a rough surface so that there is no slipping, and it's held by a string. We keep this bar using the string, and we pull the string at force F so that the bar is in equilibrium position. So what is given? The mass of the bar and its length. What we need to find? The force which must be applied at the right angle so that the bar is in static equilibrium. And also we need to find the coefficient of friction which will allow the bar to remain in static equilibrium, in stable condition. We have to find the force applied to the upper end at the right angle and the coefficient of friction on the rough surface. Well, as this is a static equilibrium, we know that some laws of physics apply to this condition. First, the vector sum of all forces acting on this object, vector sum of all forces must be equal to 0. This is the condition of static equilibrium. If it were not so, then the net force would be equal to mass times acceleration. But in this case we have no acceleration. The bar, by condition, by the statement of the problem, remains in static equilibrium. So the vector sum of all forces must be 0. And another law which applies here is the sum of all torques is also 0. Because if it were not so, if the sum was other than 0, then this object would start rotating with angular acceleration, according to the second Newton's law of rotational motion. So we have two laws of physics which obviously apply in this case. These laws apply because we consider the state of equilibrium. We consider the static equilibrium of this object. When we have to consider forces, it's always convenient to choose a system of reference, an appropriate axis, like horizontal axis x and vertical axis y. And all the forces will be considered in components. We will consider components of all forces in every direction, in horizontal direction and in vertical direction. Certainly it's possible to choose some other system of reference frame. It's possible to choose another reference frame, but whatever reference frame you choose, you will always have these conditions, and the solution, the final answer, will be the same. The final answer to the problem will not depend on the choice of the reference frame. Reference frame will just help us in consideration of this problem. So if we consider the vector sum of all forces, then the x component of all forces must also satisfy this condition. If all vectors added to one another give 0, then all the x components of these vectors will also give you 0. So we consider all the components of all the vectors, well, along the x-axis, along horizontal axis. Well, this angle is also given in this problem. This is alpha. It's also given. I have forgotten about it. And if this is alpha, then here this is also alpha. So the sum of all forces must be 0, and we first consider the x components of all forces. In order to write down the x components of all forces, we must first indicate the forces, all the forces acting on this object. The first force is given in the problem, and we must find it. Then certainly there is a force of gravitational pull, the gravitational attraction to the center of the Earth. If the rod is uniform, which is the case here, then the force of gravitational attraction will be applied to the center of this force, of this bar, the center of this rod, if it's uniform, which is implied in this problem, that the rod is uniform. If it was not uniform, if the mass was somehow distributed unevenly, then the center of mass would be displaced either to this end or to this end, and it would not be at the center. But we consider the uniform rod so that the force of gravity, the weight of this rod, is applied to the center of this rod. The center means that this distance equals L over 2. Certainly there is another force, which is the force of reaction, the force acting on the rod from the surface, the force of reaction. Let it be denoted by N. And there is a force of friction, because it's given that the surface is rough, and we need to find the coefficient of friction. So where do you think the force of friction should be directed? If there were no friction at all, then the rod would slip to the right without friction, as if it were ice. Then the rod would slip to the right. But the force of friction doesn't allow this motion. Therefore, the force of friction must be directed here, to the left. Are there any other forces acting on this object? To answer this question, you must consider all the interactions of this object, all the interactions of the rod with the outside objects, with the outside world. All the interactions. We have taken into account all the interactions. The gravitational attraction to the Earth, the reaction of the surface, the force of friction, and the pull of this string. We have considered all the interactions present here. There are no other interactions, so no other forces act on this rod. Now, as we have indicated all the forces in our sketch, we can write the condition for the horizontal components of all these forces. the horizontal component of the force of the weight of this rod is certainly 0, because the weight is directed vertically, and therefore horizontal component of this vector is 0. We will not take it into account. Also, the force of reaction N is directed vertically, so its horizontal component is 0, and we will not take it into account here. What we take into account will be the horizontal component of force F, which is equal to what? F sine alpha, because if this angle is alpha, then this angle is also alpha, and the horizontal component will be F sine alpha, because we want to know this leg in the right triangle. This force is directed in the positive direction of x-axis, so I will take it with this plus sign. It will be positive. Another force in horizontal direction is the force of friction, which is directed in the opposite direction, to the negative values of x. So this force of friction will be with the minus sign, and all this must be 0. Such are the components of our forces in horizontal direction. Only 2 forces have components in horizontal direction: the force of tension in the string and the force of friction. Other forces have only vertical direction. We have to take them into account also. The forces, the components of all forces in vertical direction must also give 0 when summed up. What are the vertical components? The force of friction has no vertical component because it's directed horizontally. We have vertical component of the force N, which is simply N, because all this vector is directed vertically, parallel to the y-axis. And it's positive because this vector looks in the positive direction of the y-axis. So N will go here as positive quantity. Then the weight of the rod, mg, directed downward in the opposite direction, so it will be negative. And then the force F will have some vertical component, which will be positive because it looks upward in the direction of positive quantities of y-axis. So it will be positive, and it will be F cosine alpha. So the first condition of static equilibrium, the condition that the net force acting on the object is 0. This condition resulted in 2 equations. One equation shows, the first equation shows that the sum of all horizontal components of vectors is 0. And another equation shows that the sum of all vertical components is 0. Horizontal components are directed along x-axis, and vertical components are directed along y-axis. So we have taken into account the first condition of static equilibrium. And the second condition is that the net torque acting on the object must be equal to 0. In order to calculate a torque, we must choose an axis of rotation. We must choose some arbitrary point about which the rod may rotate. Actually, this is an arbitrary. This is our choice. It's up to our choice which point to indicate as as the axis of rotation. It's convenient to choose this point as the axis of rotation. Why? Because two forces go through this point, and it means that the torques of these two forces will be zero, because the torque is the magnitude of the force multiplied by its arm, and the arm here will be zero. So these two forces will not be taken into account if we designate this point as the axis of rotation. We will exclude these two forces. It's more convenient when we have to take into account only two remaining forces, F and mg. Only two remaining forces will be taken into account instead of four forces. It's more convenient. It's more easy to take into account only two forces instead of four. So we choose this point as the axis of rotation, which in this case is perpendicular to the plane of this sketch. So we must write a formula for each torque. By definition, a torque M is the force times its arm. For the first force, it will be F times L, because L is perpendicular to force. No geometric functions, no sine, no cosine, just F times L will be the torque of this force, which wants to rotate the rod in clockwise direction. Clockwise directions will be chosen as positive directions of rotation, and opposite direction will be chosen as negative direction of rotation. So the force F tends to rotate the rod in clockwise direction about this point A. And the force of gravitational attraction, mg, the weight, tends to rotate the rod in counterclockwise direction. So it will come, its torque will come here, will go in with the minus sign. And in order to calculate the torque of this force, we must take the force itself and multiply it by the arm of this force. And the arm is the shortest distance from the axis of rotation to the line of action of this force. So this leg the leg adjacent to angle alpha in this triangle. The leg adjacent to this leg will be L over 2 times cosine alpha. So the arm, I need to find the length of this section. That may be found from this right triangle. It will be L over 2 cosine alpha. L over 2 is this side, and this is angle alpha. I need to find this angle, this distance. So the length of this section will be given as L over 2 times cosine alpha. This is the torque that rotates the rod in clockwise direction, and this is the torque that rotates in counterclockwise direction. That's why we have plus and minus, two different signs here. And this must be zero because of the main equation. So we have a system of three equations, three simultaneous equations, which now can be solved using mathematical methods. On this point, physics has ended. We have done everything necessary as far as physics is concerned. Now we have to use mathematics to solve these simultaneous equations. What do we need to find? We need to find here two unknown variables, the force and the coefficient of friction. The coefficient of friction will be taken into account in the force of friction, which is by definition is coefficient of friction times the force of normal reaction An. So coefficient of friction will appear in this place, in this term. Do we need to find N, the force of normal reaction? N is here and N will be here. No, we don't need N. The problem doesn't ask you to find the force of normal reaction. We don't need it. It's not required. But it's there, present in this system of equations. What can we do? We must exclude this variable which we don't need. We don't need it because the problem doesn't ask you to find N. By the way, how many unknown quantities we have in these simultaneous equations? Unknown quantities is F, which is here and here. F is unknown. Alpha is given. K is unknown, coefficient of friction. N is unknown, certainly present here, unknown quantity N. Mg is known, alpha is known, L is known. That is, we have 3 equations and 3 unknown quantities. All the 3 unknown quantities can be found, may be found from this system of equations. We can find everything, but we don't need this one, and we don't need to waste time on this variable. So we have to somehow get rid of it. How can we do it? We can multiply the second equation by K, the coefficient of friction. And then here we will have Kn and K here and K here. We have multiplied the second equation by this number. This is an unknown number, but we have the right to multiply this equation if the number is not 0. So we assume that coefficient of friction is not 0. It's most probably so. It's obviously not 0. If it was 0, then there would be no condition of equilibrium of this rod. The rod would slip to the right if it was not 0. But the surface is rough, it's given, so the coefficient of friction is surely not 0. And so we have the right to multiply this equation by K. And now we notice that we have this term Kn here and similar term in the first equation. So if we add first equation to the second equation, then this term will vanish. It will disappear. So we add these 2 equations. And what will be the result? The result will be F sine alpha minus Kn, but that will be balanced by plus Kn. So this term will cancel. And as we add 2 equations, then we will have to write here minus Kmg and plus Kf cosine alpha equals to what? 0 plus 0. So this equation contains no N. We don't need N, and we got rid of it. Also, we can take the last equation here, and that will be the new system of equations. But now we have 2 equations and 2 unknown quantities, F and K, instead of 3 unknown variables. We have only 2 in the remaining 2 equations. The force F can be found from the first equation immediately. If we look at the first equation, we find that L will cancel, and F from here, F equals mg over 2 cosine alpha. That's, by the way, the final answer. We have found this unknown quantity F from this equation immediately. So we have found the answer. Is it the end of the problem as far as the force is concerned? We have found the force. So can we now quit and go away? No. We have to analyze this answer. Analyzing the answer is a necessary step in solution of any problem. How should we analyze the answer? First, we have to make sure that the dimension gives us, the dimension of the obtained formula gives us the dimension of the force. What about the dimension here? mg, what is this? This is force. This is measured in newtons. That's what we need here. Is it always the case? No. Sometimes we may make a mistake somewhere. We may forget some variable, and so we may obtain a wrong unit of measurement, a wrong dimension. Sometimes it happens. So you have to analyze the dimension of your formula which you have obtained. Always analyze the dimension. The units of measurement must coincide. The right side of this equation should give you the units of measurement needed by the left side. And then, when we have verified the dimension are reasonable, whether the predictions are realizable in practice. Well, what can be done to analyze this formula? Suppose alpha is 0. Suppose this rod is almost lies on the surface, and we just started to lift it, pulling by the end. Alpha is almost 0, it tends to 0. What should be the force F equal to? It's obvious that it should equal to mg, to half the weight of this rod, because another end of this rod is supported in this point, and we just pull by this end, and the weight is applied to the center. So F should be mg over 2, half the weight of this rod. So that's quite reasonable. We obtained mg over 2, which gives a reasonable result. If alpha is 0, then cosine alpha is equal to 1. In this case, for alpha 0. And we obtain the correct result, which is obvious without solution of this problem, without even solving the problem. We understand that in this case, when alpha is 0, the force F must be half the weight of the rod. This is obvious, and we obtained it, and our formula gives this result. Another limiting case is when alpha tends to 90 degrees. When alpha tends to 90 degrees, when this angle is almost the right angle, so the rod stands almost vertically. In this case, you don't need even to pull the string. The force will tend to 0. It's obvious. If the rod just stands vertically, you must apply 0 force in order to keep it vertical. So it's exactly what the formula gives. If alpha is 90 degrees, that cosine alpha is 0, and the force will be 0 in this condition, in this position of the rod, in vertical position of the rod. The force must be 0, and that's exactly what gives you this formula. So the formula satisfies this verification procedure. We test this formula for physical sense, whether the formula is reasonable or not, whether it gives you reasonable results in different situations. When something goes to 0, or some other variable goes to infinity or goes to 90 degrees, etc. You always analyze the formula for physical sense. Whenever you obtain any solution, you analyze it first for its dimension, and second, whether the formula is reasonable. Only after such analysis you can be sure that the formula obtained is correct. Can you be 100% sure? No. Sometimes you have correct units of measurement, and the formula seems to give you correct results in any situation, but the formula may be incorrect. For example, suppose we have cosine square. All the analysis which I performed will give you the same results. If alpha goes to 0, the force tends to mg/2. And if alpha goes to 90 degrees, again, the force will be 0. The same as before, but the formula will be incorrect. So even if you carry out all this analysis and the analysis suggests that the formula is correct, even if your analysis suggests that the formula is correct, then you cannot be 100% sure that the formula is correct. Sometimes there are such mistakes which cannot be discovered using such an analysis. But anyway, such analysis is absolutely necessary. You have to analyze the formula for the units of measurement and for physical sense. At least these two steps must be carried out. But even these two steps sometimes don't guarantee that the formula obtained is correct. Sometimes there is such a mistake which cannot be discovered using these two methods. But in many cases, in most of cases, these two methods of analysis, two steps in analyzing the formula will produce good results, and most of mistakes will be discovered by looking into the units of measurement and by testing the formula for physical sense. In most of the cases, but not always. Okay, we have found F. We have found the force with which we have to pull the string in order to keep this rod in a stable, static condition. But we have also to find a coefficient of friction, which can now be found from here, from the last equation. Coefficient of friction is here and here. So I can write this equation in such a way that these two terms will go to the right-hand side of this equation, and that will give me k mg minus f cosine alpha. And now I can immediately obtain the coefficient of friction k from here. That will be f sine alpha divided by mg minus f cosine alpha. F should be taken from the first formula. So we have to substitute this for F. We have to substitute this formula for F, and that will give us what? mg sine alpha cosine alpha divided by 2, and here we will have mg minus mg cosine alpha divided by 2. mg can be cancelled. And then we obtain sine alpha cosine alpha divided by 2 minus cosine alpha. That's the answer for the coefficient of friction, which we have to find in this problem. Again, we have to analyze this answer. Sorry? Where 2 minus? Here is the minus. Huh? Yes, you're sure. Yes, certainly. Cosine square, yes, certainly, yes. Cosine times cosine, that will be square and square. Yes, absolutely. So again, to analyze this solution, we have to check the dimension. Coefficient of friction is dimensionless quantity. And the formula obtained is also dimensionless. No units of measurement, just the number. That's okay. And now we have to analyze it for a physical sense, a physical reason behind it. Well, in order to do it, it would be convenient to somehow change this formula. I multiply it by 2, this one and this one. And 2 sine alpha cosine alpha will be sine 2 alpha divided by 4 minus 2 cosine square alpha. Why this is more convenient? Well, certainly you may analyze this formula too. But for me this is more convenient because when alpha goes to 0, sine 2 alpha is also 0. And when alpha goes to 90 degrees, then 2 alpha will be to 180 degrees, that is pi. When alpha is pi over 2, 2 alpha will be pi. And in both cases sine is 0. So the coefficient of friction will be 0 when alpha goes to, well, alpha is 0, and when that is when the rod is horizontal, and when alpha is pi over 2, when the rod is at the right angle. In both cases, you need no friction to keep the rod in static condition. You need no friction here and here. That seems to be reasonable. As far as cosine squared is concerned, it is 0 when alpha is pi over 2. So in this case, the denominator will be just 4. But the maximum of cosine squared is 1. So the minimum of this denominator will be 4 minus 2. The minimum value will be 2. It's good because when you have something minus something, there is always the possibility that the denominator will turn into 0. But this is not the case. This expression will never be 0 in denominator, so that's okay. That's okay, it will never be 0. 0 in denominator is always an alarming indicator that something is wrong, because if you have a 0 quantity in denominator, then the whole formula will give you infinity. And there are no physical quantities which go to infinity in real life. Any physical quantity is finite. So any infinity which you ever may obtain is an alarming indicator that something is wrong in your solution. But this is not the case here. Our denominator will never turn 0. And it seems to be quite reasonable. It seems to be quite reasonable. But there is one thing to be discussed about this coefficient of friction. There is one thing. We see from this formula that coefficient of friction depends on alpha. It's not constant. It depends on the angle of inclination of your rod. So the coefficient of friction is not constant. But that is usually the case. The coefficient of friction, as I told you, is defined by this formula. The force of friction is coefficient of friction times force of reaction. Force of reaction may be constant. For example, we take this object. Its weight is balanced by the force of reaction. The weight is directed downward and the force of reaction from the table surface is directed upward. So these two forces are balanced. Is there any force of friction now? No. No horizontal forces of friction act on this object. If there were any horizontal forces, this would accelerate, but it doesn't accelerate. So there are no horizontal forces. Suppose I start pushing this object slightly sideways. If I apply only a small force, then it will not move. It will stay where it is. Because the force I apply here will be balanced by the force of friction directed in the opposite direction. These two forces, force of friction and the force with which I act on this object, will be balanced. But if I apply a larger force, then it will move. So the force of friction in this simple experiment varies from 0 now to some maximum value now. And in between, the force of friction varies from 0 to some maximum value. So the force of friction and coefficient of friction will be something like that. If I show here the force applied, an external force applied, and here a coefficient of friction, then when the external force is 0, the coefficient of friction is also 0. And when the force applied grows, the coefficient of friction grows. And the force of friction balances the applied force. When the applied force is not very large, the force of friction is enough to balance the applied force. They are always equal. The force of friction is equal to the applied force. But that will not, that situation will end when the force of friction has some maximum value. That is the applied force equal to the maximum value of the force of friction. And then the force of friction will not grow anymore, and any larger force will result in acceleration of the object, but the force of friction and coefficient of friction will remain constant and will be the same. So, I may apply larger force and the object will move with large acceleration, but the force of friction will remain the same. But in between these 2 points, the coefficient of friction may vary from 0 to maximum possible value, which is given by this formula. The coefficient of friction varies from 0 to some maximum possible value. In this particular problem, the rod will not necessarily slip sideways at any particular angle. It may remain always at the same point. So this formula may give you a varying coefficient of friction, which will never reach its maximum possible value. So in our process, the coefficient of friction may vary from 0 to some maximum value, but the slipping will never occur. The slipping, at no coefficient of friction, there will be slipping. The coefficient of friction will vary, but we will never reach the situation when the rod slips on the surface. We will go along this section of this curve. So, any questions as far as this problem is concerned? I'm trying to explain everything in detail so that no minute detail slips your attention, so that you understand every little thing in solution of such problems. Okay. Next problem will be number 206. A heavy spool with a thread wound on it lies on a rough horizontal surface over which it can roll without slipping. So there is a heavy spool with a thread wound on it. If the thread is pulled to the left, in a horizontal direction, the spool will also move to the left. It's obvious. It will roll to the left. If the direction of the thread is changed, the spool will begin to roll to the right at a certain angle. So if we pull, the thread is wound here, and the diameter of this part is small r, and if we pull the thread in some direction at certain angle alpha, the spool will begin to roll to the right. The spool will begin to roll to the right. The problem says that angle alpha is the angle between the direction of the thread and a vertical line. So it's not the angle with a horizontal line, it's the angle with the vertical line. Well, it's practically very little difference. It depends on what you denote by alpha. So there is a vertical line, and angle alpha is between vertical direction and the direction of the thread. Determine this angle at which the spool will start rolling to the right instead of rolling to the left when you pull in this direction. Determine the angle. What will happen to the spool at the given value of this angle? The radius of the spool head is r, and this is capital R. The radius of the larger spool is capital R, and there is a radius of the smaller part where the thread is wound. Yes, that's correct. That's correct. The same picture, yes, is indicated here. The same picture. So, if we pull this string horizontally to the left, the spool will roll to the left and move to the left. But if we change the angle of the string and pull at some unknown angle, which we have to determine, the spool will not roll to the left and will not roll to the right, but will roll on remaining on the same point here, on the same place. The center of mass will not move. But if we change the angle further to the right and pull almost horizontally to the right, then the spool will go to the right and will roll in different direction. So we have to find this angle. If angle alpha is smaller, then the spool moves to the left. If angle alpha is larger, then the spool moves to the right. to the left and to the right. And we have to find this intermediate value for angle when the spool does not move at all. It's only rotating, not moving. So when the center of mass of the spool does not move, there is no translational motion of the center of mass. Only rotational motion will be present. Then, in this case, if the center of mass is at rest, then the vector sum of all forces acting on the object must be 0. So this is the condition for the center of mass to remain at the same place. If this condition is violated, if the sum of all forces is not 0, then the sum of all forces will be equal to the mass of the spool times acceleration, according to the Newton's second law. But due to conditions of this problem, under the conditions, the center of mass is at rest. It doesn't move. So we have to use this law of static equilibrium. However, in this particular case, the spool may rotate and will probably rotate, and with slipping here. And rotation means that the total torque applied to the spool is non-zero. So the second condition which we used last time, that the total torque is 0, will not apply in this particular case, because when we pull the string at this particular angle alpha, the spool will rotate. It will rotate, but the center of mass will remain at the same place. So we have to use the first condition, but we don't use the second condition. It will be non-applicable in our problem. Okay, in order to use this condition, we have to indicate all the forces acting on the object. All the forces. There is the force of gravitational pull, mg, if the total mass is m, and there is the force of normal reaction of the surface, and the force of friction if the spool rotates in this direction. Then the force of friction acting on the spool will be directed oppositely its velocity. That will be the force of friction. And also the force of tension in the string. Let it be T. Have we taken into account all the forces? In order to answer this question, we must recall that a force is a measure of interaction. So in order to find forces, all the forces, we have to find all the interactions of this object with the outside objects. All the interactions. We have taken into account the interaction with the string, the interaction with the earth, and the interaction with the surface. The interaction with the surface gives you two forces, the force of normal reaction and the force of friction. These are two components of the total force of interaction with the surface. Any other interactions? No. With the string, with the earth, and with the surface. No other objects act on this spool. So we have taken into account all the forces. It's always important to take into account all the forces. If you miss only one force, if you forget about it, the solution will be wrong. So again, in order to use this vector equation, we must consider components of forces. And in order to consider components, we must choose some reference frame, some axes like x and y, some perpendicular axis giving a reference frame for this particular problem. And in this reference frame, we will consider the components of all forces, and we will write this condition for two components, for x component and for y component of each force. So let's consider the x component. That is horizontal component of all forces. Obviously, the weight mg has no horizontal component because this vector is directed downward. Also, the force of normal reaction is directed vertically. It has no horizontal component. It's better to say that the horizontal component is 0. So we don't take it into account when we consider the horizontal components of the forces. But horizontal components will be present for the force T, horizontal component, and it will be positive because the force T is directed in the positive direction of x-axis, has positive direction. So T times sine alpha, that will be the horizontal component of this force. So I just draw it separately. Here is the force T, and here is its horizontal component, and this is angle alpha. So from this right triangle, we have that horizontal component of the force T is T sine alpha, positive, because it's directed in the positive x, and minus this negative force, which is horizontal. All the force of friction is horizontal, and this force of friction equals coefficient of friction times the force of normal reaction, and it will go with a sign minus, and that must be 0. And now in vertical direction, the same. We have to take into account this condition that all the vector sum of all forces is 0. It means that the sum of all vertical components of all vectors must be 0. All vertical components. First, the vertical component of the tension in the string. It must be T cosine alpha, this vertical component of the force of tension, T cosine alpha. It goes with a plus sign because it's directed upward in the positive direction of y-axis. And then other forces will have vertical component, and the force of normal reaction will go with a plus sign because it's directed upward in the positive direction of y-axis, and with a minus sign, the weight of this spool directed downward, minus mg equal to 0. So this condition of static equilibrium, the condition that the center of mass of our object does not move, remains at rest. This condition results in two equations, one for x-axis, another for y-axis. Now suppose that we pull the string at such a force which is not very large. We pull the string at such a force that the spool does not rotate under this force. We can pull slowly with small force, applying small force. Then the spool will not rotate. It's obvious. The spool will start rotating if we pull with large force. Then the spool will rotate, and its center of mass may remain at the same place. But if the spool does not rotate, if we pull at a small force T, then we must use exactly this condition. If and only if the force T is not very large, then if it's small force, then the spool will not rotate. It will remain at rest, both the center of mass at rest and no rotation. If no rotation, then this equation must be taken into account. At first I took this problem for another one where the spool was actually rotating. I considered several problems for today's lecture. But in this problem, the spool will not rotate. It's somewhat easier. So if it will not rotate when the tension in the string, when we pull the string using the small force, just slightly pull the string, then the spool will not rotate, and then we have to use this equation anyway. This equation means that the total torque acting on the spool is 0, and the total torque is easily calculated if we take the axis of rotation, if we take the center of mass for the axis of rotation, then the force F will try to rotate in clockwise direction, so it will be F, force of friction, which is Kn, times the arm of this force, which is R, capital, minus force T, which tends to rotate in counterclockwise direction, in the opposite direction. So it will go with an opposite sign. Force T times the small radius, T small radius, must be equal to 0. That is when the spool does not rotate. Yes. If we pull the string using the small force, if we apply small effort, then the spool will not rotate. And in this particular case, we have to calculate the torque of the force of friction Kn, and the torque is always the force times the arm of the force. The arm of the force here is large radius, capital R, minus the force of tension in the string times the arm of this force, and the arm of this force is the small radius, small r. These two torques have different signs because they tend to rotate the spool in different directions. So we have these equations, and what can they do? What can they give us? What we need in this problem? Do we need to find the force T? No, we don't need to find N. We don't need to find coefficient of friction. What we need to find is alpha in this problem. So we have some equations which must somehow be tackled and solved to find the condition for alpha. Well, again, we don't need N here. We can get rid of N. For this purpose, we will multiply this equation by K. K here, and then add these two equations, the first one and the second one, so that this term will cancel with this term. That will give us t sine alpha, what remains from the first equation, plus kt cosine alpha, and the next term cancelled, minus kmg equals 0. That's the result of adding two first equations. We got rid of this n. We don't need it. Okay, and the last equation still contains n and k. Still contains n and k, which is the force of friction, here, which can easily be found from this equation. If we need it, we can find it. It's T small r over capital R. If only you need the force of friction, you can easily find it. Well, what I think about now is that, yes, all this is absolutely correct, and it's possible to find the solution of the problem by analyzing these equations. However, it occurred to me that there is a much simpler way to solve this problem, without all this algebra and without all these equations. In this particular case, there turns out to be a much simpler way to solve this problem. Nobody knows, without any equations, without any algebra. Yes, there is a much simpler way and much quicker way. Let's discuss it now because it's very interesting. I will draw the picture again so that it will be more clear. So here is a force of normal reaction, N, and a force of friction acting on the spool, F, and here is the force of tension in the string, and this is small r, and this is larger R, capital R. So I have considered in this problem the center of mass as the center of rotation, as the axis of rotation. It would have been much more easier if we considered the axis of rotation going through this point. It's better to use this point as the axis of rotation because there are two forces going through this axis and going through this point and having the zero arms. The arm of the N force is 0 and the arm of the F force is 0. So we don't have to take into account the torques of these two forces. If we choose this point as the axis of rotation, then we don't have to take into account the torques of these two forces, which makes it more easy, much more easy to solve the problem. In this case, only one force will have a torque equal T. The torque will be equal to the force times its arm. And what is the arm of the force? The arm of the force is the smallest distance between the line along which the force acts and the axis of rotation. That is the arm of the force T if the axis of rotation is here. So if the spool does not rotate when we pull the string at certain angle alpha, it means that the torque of this force is 0 if we calculate the torque with respect to this axis. It means that the force T must be directed in such a way that the line of action of this force goes through this point. That is the geometrical condition for the spool to remain at rest without any rotational motion. That's it. Only notice that if you choose this point as the axis of rotation, then the two forces F and N will have 0 torques. And so the remaining force T must also have 0 force so that the spool doesn't rotate. Under the condition of this problem, the spool doesn't rotate when we pull the string at angle alpha. So in this case, the string must be directed in such a way as the line of the string, that the line of the string should pass through this point. That's it, the geometrical consideration without any equations. The equations are correct, but you need some algebra to solve these equations. And the solution of this problem turns out to be much more simple. So from this right triangle, this angle is right, we can immediately find angle alpha. That is the angle alpha between the line along which the string is pulled and the vertical direction. We have to find this angle alpha. And we can easily see that the sine alpha is the opposite leg to this capital R, to this large radius. That's the solution, the simple and direct solution, immediate solution. We immediately obtain the solution. We need to find angle alpha, and we have found it. We have found it from simple geometric consideration. Because the string must be pulled in such direction that the line of the string coincides with this, passes through this point. Why? Because this force must have no torque. It must not rotate the spool. And the axis of rotation is this one. And if we choose this axis of rotation, the other two forces, force F and force N, will have 0 torques. And in this condition, we know that the spool doesn't rotate. So the torque of the remaining force must also be 0. That's very simple consideration and the immediate solution of this problem. Originally, I wanted to solve somewhat more complicated problem where accelerated motion of this spool is involved. But as I have chosen a more simple problem for this lecture, the more simple solution is there. It's better. It's better than trying to solve equations. Yes, certainly you can go this way without any doubt. You can go this way. You can solve these equations algebraically. I'm absolutely sure you will get the same solution. Absolutely sure. But algebraic way is much more lengthy and complicated than the simple geometric consideration, which gives you immediately the correct solution to this problem. Well, sometimes looking carefully at the picture helps you a lot to find the proper solution. Sometimes a good picture facilitates solution in such a way that, well, you immediately obtain the solution instead of solving 3 simultaneous equations, algebraic equations. That's it. Any questions? Well, we have just 5 minutes before the end of this lecture, and in conclusion, I wanted to tell you that according to an administrative decision, all the universities in Moscow are closed starting Monday, and all the students will go to distance studies in Moscow. We are in Moscow region, but nobody still knows, nobody knows whether this decision will be somehow applied to our university. It's very probable that starting from Monday, you all will be on distance studies. If this happens, no problem at all. You will be like other students now from other countries, well, sitting at home and watching my lectures transmitted by this system of video. You may watch the lecture in during the time of the lecture, or you may find it later on the YouTube. It will be there. It will be posted there. So for you, it will be probably even better, because you will not be required to be present at this exactly this time at the lecture. You will have the right to choose any time convenient for you to watch the lecture, to attend it distantly. But if we are on distant learning, I still don't know how can we organize the mid-semester written test. Probably it will be conducted distantly in any situation, whether we are transferred to distant studies or not. Anyway, it will be conducted distantly. I will think about it, and I will make announcement later. So on this, let us finish this lecture on this point. Thank you all.